So, good afternoon. So, the topic of today's discussion is thermodynamics. Okay. So, let's start with the topic. We already completed part 1 of the discussion. So, today's discussion is part 2. Okay. Today's discussion is part 2 of thermodynamics. Part 2. Okay. I hope everyone is visible. Okay. Fine. So, let's begin. So, we are planning to conduct today's session in this much topics. First one is zeroth law of thermodynamics. Second is what is heat, work, internal energy, and all. Next, then it is first law of thermodynamics. Then second law of thermodynamics. Then what is reversible process and irreversible process. Then after all, then we will discuss about heat engine. That is our heat engine. Then refrigerator and Carnot engine. Okay. So let's see. So we can begin the session with zeroth law of thermodynamics. Zeroth law of thermodynamics. Before, I hope everyone know what is thermodynamics and all. I already discussed thermodynamics is a branch of physics which deals with study of heat and temperature. Okay, and interconversion of heat into other various forms. First of all, I hope everyone know what is a system. System is a part of universe in which is under observation. System is the part of universe under observation. System is the part of universe under observation. And surrounding is the part of universe. Surrounding is the remaining part of universe. Surrounding is the remaining part of universe other than system. So remaining part of universe. Okay. So I hope everyone know what is system and surrounding. Okay, fine. So let's see what is zeroth law of thermodynamics actually means. Zeroth law of thermodynamics means it means when two systems are said to be thermal equilibrium, then they have same temperature. That means when two system, this is one system, this is another system, this is first one, this is second one. Okay, if the system 1 and system 2 is said to be in thermal equilibrium, if it is said to be in thermal equilibrium, then T1 is the temperature of system 1 and T2 is the temperature of system 2, then T1 will be equal to T2. Okay, fine. That is thermal equilibrium. Okay, thermal equilibrium means T1 is equal to T2. Okay, as per zeroth law of thermodynamics, if two systems are thermal equilibrium with the third system separately, then I'll explain. See, if two systems T1, sorry, S1, S2, and this is S3. As per zeroth law of thermodynamics, if S1 is thermally equilibrium with S3 and S2 is thermally equilibrium with if S1 is thermally equilibrium with S3 and S2 is thermally equilibrium with S3, then S1 and S2 is also in thermal equilibrium. Okay, fine. That means if two systems are thermally equilibrium with the third system separately, then they will be the remaining two systems will be also in thermally equilibrium. That is, S1 is thermally equilibrium with S3 and S2 in thermally equilibrium with S3. Then S1 and S2 will be also in thermal equilibrium. Simple. Okay, I hope everyone. This is the basic law. No need to know much about. Okay, that means So that then the temperature in S1 is T1 and S2 temperature is T2 and S3 temperature is T3. T1, T2, T3 will be same. Fine. So I am writing the definition of zeroth law of thermodynamics. If two systems are thermally equilibrium with the third system. If two systems are thermal equilibrium with a third system, then they are also in thermal equilibrium. Okay. If two systems are equilibrium with the third system, then that two systems will be also in thermal equilibrium. Simple. Okay, fine. So next we can see what is let's see some properties. Okay, let's see some properties. Okay, I'm writing here. Okay, let's see some properties of thermodynamics. Okay, some thermodynamics properties. Some thermodynamic properties. First one is intensive property and extensive property. Intensive and extensive. Intensive property means this is actually independent of the size of the system. These are independent of size of the system. But extensive property depends on the size of the system. Okay. Intensive properties are example temperature, pressure, etc. Extensive properties are example mass, volume, etc. Okay. Internal energy, enthalpy. Okay. So let's see some thermodynamic variable. For example, first one is path function. Path function means these are variables. Path function means these variables are dependent on the path. These are path dependent functions. Path dependent variables. Example, heat and work. Okay. State function means these are independent of path. That means these functions or these variables does not depends on the path. Instead, they depends only on the initial and final state. They depends only on initial and final state. Example, internal energy, volume, pressure, temperature, etc. Okay. I hope everyone understands. Okay. So let's see. What is internal energy? What is heat? What is work? Okay. This is the next topic. What is internal energy? What is heat? What is work? I already told you actually heat means heat is a form of energy that is transferred from one system to another system in the part 1 itself. Okay. Now let's see what is internal energy. Internal energy means it is a sum of all kind of energy in a thermodynamic system. It is a sum of all kind of energy. Sum of all energy in a thermodynamic system. In the last class, I already told how to find internal energy. U is equal to F by 2 RT. F by 2 RT. U is equal to F by 2 RT. F means degree of freedom. Degree of freedom. Okay, fine. For example, for a monatomic degree of freedom will be 3. For diatomic degree of freedom will be 5. Okay. Now, let's see work. To measure work, uh, uh, we know how to measure work. We know how to measure work. The equation to measure work is delta PV. We can, okay, fine. At a constant pressure, it will be P delta V. P delta V. Okay, fine. So we should understand that the science in work, okay, how to give negative and positive. Work done, work done by the system, or expansion, work is positive. Work done on the system or work done on system or compression work is negative. Okay, I hope everyone understood this much things. Okay, fine. So I hope everyone is clear about this much topics. Okay. Now let's move to first law of thermodynamics. First law of thermodynamics. As per the first law of thermodynamics, we know the heat supplied to the system is partially used to increase the internal energy and the remaining is used to done the work. Okay, fine. So the heat given to the system is used for what? Increase the internal energy and for doing work, or and the remaining or the rest is used to work done on the surrounding or environment. Okay. So delta Q is equal to delta U plus W. That is the first law of thermodynamics, and it is based on law of conservation of energy. Based on law of conservation of energy. Law of conservation of energy. So it is based on law of conservation of energy. Delta Q is equal to delta U plus delta W. Fine. So we know W is equal to P delta V. So delta Q is equal to delta U plus P delta V. Fine. So let's see. When in a question for sign conventions, we should understand how to give signs. Okay, negative, positive signs. If we are giving heat to the system, heat is supplied to the system. That means Q is positive. Heat liberated from system, delta Q is negative. Okay, Q is negative. Internal energy increases means delta U is positive. Internal energy decreases means delta U is negative. Fine. Work done by the system positive, work done on system negative. So I hope everyone is clear about the sign conventions. Okay. So okay. See, in the last class, in the last classes, not in the last class, in the previous so many classes, I already told what is Cp, Cv, and all. Cp by Cv is gamma, and Cp minus Cv, May's relation, that is May's formula, that is Cp minus Cv is R. We need this formulas, okay. Cv is R by gamma minus 1. So this much things we need, okay. Okay, fine. I want this equation to solve the remaining questions. So in the coming questions, so everyone should understand Cp, Cv, gamma relations and all. Okay. So let's study some thermodynamic processes. Okay. Some thermodynamic process. First is isothermal process. That means at isothermal process was isothermal. Okay, isothermal process. At isothermal process, that is temperature is a constant. Temperature is a constant. Sorry, temperature is a constant. Temperature is a constant. T is a constant. T is a constant. T is a constant. T is a constant. So delta U is equal to 0. We know delta U is a function of temperature. Delta U is equal to 0. Fine. So W is equal to delta Q. Or delta Q is equal to W. So what we understand in isothermal process, the heat we are giving to system is completely used to do. There is no internal energy change. Okay, there is no internal energy change in isothermal process. The entire heat we are giving to the system is used to do work. Okay, fine. And we know in isothermal process P by V, P proportional to 1 by V, and PV is a constant. PV is a constant. That is the PV is a constant. That is the equation of isothermal process. And we should know how to find work done in isothermal process. Work done in isothermal process. I know now I'm not deriving the equation. I know everyone know how to derive the equation also. We just want to know the equation only. That is W is equal to 2.303 nRT log V final minus V initial. Okay. This is the work isothermal. Okay. This is the work isothermal. This is the work isothermal. Okay, fine. In isochoric process, we know V is a constant and delta V is equal to 0. So P delta V will be 0. So work will be 0. So entire heat we are giving to the system will be used to increase internal energy. And we know internal energy is equal to at a constant volume. We know the how to find internal energy, the NCV delta T, NCV delta T, and we know CV is R by gamma minus 1. So we can write delta Q is equal to delta U is equal in isochoric process. Okay, isochoric. In isochoric process, in isochoric, delta Q is equal to delta U because delta V is equal to 0. So P delta V is equal to 0, W is equal to 0. So delta Q is equal to delta U, which is equal to NCV delta T, and CV is equal to R by gamma minus 1. So NR gamma minus 1 delta T. So next one we want to know about isobaric. In isobaric, I'm not going to isobaric. Isobaric the same one. Like in isobaric, I'm just writing the equation only. In isobaric, delta Q is equal to delta U plus W, which is equal to delta Q is equal to NCP delta T, NCV delta T, and P delta V. P delta V we can write NR delta T, NR delta T, NR delta T. Okay, this is the relation in isobaric process. Isobaric process. Okay. So now just we want to move. We want to know about adiabatic process. Our most important process is adiabatic process. Adiabatic process. That is the most important one. Adiabatic process. Adiabatic process. Adiabatic process. Adiabatic process. Adiabatic process. In adiabatic process means there is no heat exchange. There is no heat exchange. There is no heat exchange between system and surrounding. Between system and surrounding. There is no heat exchange. System and surrounding. So that means there is heat is not transferred between system and surrounding. That means the system and surrounding is actually covered with an adiabatic wall. Okay, adiabatic wall. So which does not is not permeable to heat. So, which means which does not allow heat to pass from system to surrounding. Okay. Instead of saying adiabatic process, in the questions it can be given as like see in questions it may not say adiabatic process. Instead of saying adiabatic process, they can say sudden bursting, sudden expansion. Okay, that is like one second. So instead of saying adiabatic process, the question may be given as a balloon bursts suddenly or a system expands suddenly. Okay. Instead of saying adiabatic process, the question may be given as example. It may be given as sudden bursting, sudden expansion, etc. Sudden compression, whatever. Okay, fine. So in adiabatic process, Q is equal to 0. So delta U is equal to minus W. Delta U is equal to minus W. Okay. So delta U is equal to minus W. What is actually this means? Delta U is equal to minus W. Delta U is equal to minus W. That means during adiabatic expansion, so during adiabatic expansion, that means work is increasing, delta U is decreasing. So adiabatic expansion, internal energy decreases, temperature decreases, or we can say during adiabatic compression, internal energy increases, temperature increases. Okay, fine. That is a sign actually meaning. Okay. So we want to know the relations and okay, we want to know the equations of adiabatic process. We want to know the equation of adiabatic process. Equation of adiabatic process. Okay, fine. In isothermal process, we saw PV is a constant. In adiabatic process, PV raised to gamma is a constant. Okay. The equation of adiabatic process is PV raised to gamma is a constant. That is our equation. PV raised to gamma is a constant. Or I can write TV raised to gamma minus 1 is a constant. Or I can write P raised to 1 minus gamma, T raised to gamma is a constant. Okay. These are the three equations. These are the three equations. Okay. PV raised to gamma is a constant. TV raised to gamma minus 1 is a constant. P raised to 1 minus gamma, T raised to gamma is a constant. Okay. So we saw in isothermal process, PV is a constant and work isothermal is equal to 2.303 nRT log V final minus V initial. So what is the work done in adiabatic process? How to find that? The equation is nR T initial minus T final, T initial minus T final, gamma minus 1. Okay. That is the equation. What is gamma? Cp by Cv. Gamma is the specific heat capacity, molar heat capacity ratio. That is Cp by Cv, gamma. Okay. nRT initial minus T final divided by gamma minus 1. That is the work adiabatic is equal to nRT initial minus T final gamma divided by gamma minus 1. Okay. One more thing. Bulk modulus of isothermal process. I already told in the last class, bulk modulus of isothermal process is pressure. Bulk modulus of adiabatic process is gamma pressure. Okay. These things. I'm repeating the equations because we used bulk modulus of isothermal process and bulk modulus of adiabatic process in our waves chapter, that Newton's law and Laplace correction. Laplace told that bulk modulus of velocity, like that propagation of sound through air, is adiabatic process, not isothermal process. In there we use bulk modulus in as isothermal bulk modulus as pressure, which is used by Newton, and Laplace corrected us. It is not isothermal process and it is adiabatic process. So bulk modulus adiabatic is gamma pressure. So I hope everyone is remembering those things. Okay. So fine. So far so good. So far so good. Okay, fine. So let's see. What is other next topic. Okay. So I want to know what is a cyclic process. We know what is a cyclic process. Cyclic process means a thermodynamic system returns to its initial state after a series of changes. A system moves from a point A. Suppose a system moves from a point A and it goes through B and it goes to C and it goes to D and it comes back to A. That means after a series of changes, the system coming back to its normal state. That is called a cyclic process. Cyclic process. And we want the cyclic process in Carnot engine. Okay, cyclic process. Okay. So now let's see what is reversible process and irreversible process. What is reversible process and irreversible process? What is reversible process and irreversible process? Reversible process. What is reversible process? Means it is a very slow process. It means a very slow process. Very slow process. It is a very slow process. We can say infinitely slow process or a quasi-static process, whatever. Okay, in which system and surrounding always will be in equilibrium. System and surroundings will be surrounding will be surrounding will be in equilibrium. System and surrounding will be in equilibrium. System and surrounding will be in equilibrium. Reversible process. Okay, it takes in both the forward and we know reversible process which it will take place in both the forward and backward direction. Okay, and reversible process is actually a ideal process which we cannot see so in our real life. Almost the process we are seeing is irreversible process. Okay, uh, in reversible process we don't want to make any we don't want to make any change in the surrounding, make the system back to its normal, like without changing without making any change in the surrounding. We can without we don't want to put any external things, any external changes in the system or surrounding, to make the process back to the normal state. Without doing anything, the system will come back to its normal state. That is reversible process. But in case of irreversible process, this process attains a final state. Means it attains a final state. Okay, it attains a final state from initial state. Okay, I'm not saying it is a fast process, but comparing to reversible, it is fast. Okay, there is no equilibrium. There is no equilibrium between system and surrounding, and it is one. It is a real process. It is a real process, and we can see in our day-to-day life. Okay, and it is we cannot brought the system back to its initial state without making any change in surrounding. Like we want to make some changes to the system or surrounding, then only uh, we can brought the system back to the normal state. Okay, fine. Like it is not so important. We want to know what is the reversible and what is the reversible process. So it is good if we know it. Okay, fine. So we completed thermodynamics, zeroth law, heat, work, internal energy, first law of thermodynamics, second law of thermodynamics. Now second law of thermodynamics is remaining. Okay. So we want to see what is second law of thermodynamics. Okay, let's see what is second law of thermodynamics. And heat engine is actually based on this second law of thermodynamics and all. Okay, fine. Second law of thermodynamics. Second law of thermodynamics. As per the second law of thermodynamics, no, actually, second law of thermodynamics contains two statements. Kelvin-Planck statement and closure statement. Kelvin-Planck statement and closure statement. As per the Kelvin-Planck statement, Kelvin-Planck statement, Kelvin-Planck statement, Kelvin-Planck statement, no process is possible whose sole result is absorption of heat from the reservoir and complete conversion of heat to work. That means it's saying it is impossible. It is almost it is impossible to completely convert the heat from a hot reservoir, heat from a reservoir to work. It is like we are giving a heat to a system. Okay, like we are giving heat. Okay, as per Kelvin-Planck statement, it is impossible. It is impossible to convert. It is impossible to convert the complete heat we are providing to for work done. So when we are giving a heat, it will like it only a part of heat will be used for work, and there will be heat loss. Heat loss will be there. It is impossible to convert the complete heat we are giving to produce work. Okay, means there will not be 100% efficiency. I hope you understand. Okay, what is closure statement? Closure statement. As per closure statement, no process is possible whole is transferred of heat from cooler object to hot state of work done. That means we cannot move heat from cold temperature to hot temperature. That means we cannot transfer heat from cooler object or cooler reservoir to hotter reservoir or hotter object without doing external work. That means to move heat from a cooler object. This is a cooler object and this is a hotter object. Cool, hot. To move heat from cooler to hotter, we should do external work. That is closest statement. And heat engine based on Kelvin-Planck statement. Heat engine is based on Kelvin-Planck statement. Refrigerator is based on Closey statement. Okay. What is heat engine? Heat engine means oil is there at a it contain working substance. It contain working substance. So when we are giving Q heat from hot produce a work W and it goes at temperature of Q1 and this is Q2. Okay. So apply Q1 heat and using that Q1 heat, the working substance work and produce a work of W and lose the heat of Q2 to the cold reservoir. Okay, fine. I hope everyone understand heat engine. So what is the output? Output is our work. What is the input? What is the input? The thing that is we given to system. We give what is the input? Input is input input is Q1. Q1 is the input. Q1 is the input, and output is W. And heat engine. Heat engine. We can write Q heat engine. Heat engine. Okay. Heat engine. Heat engine. Like output is output. Output is W. Input is Q1. So efficiency, eta efficiency, output by input, that is Q W by Q1, W by Q1, which is W is equal to, we know, Q1 minus Q2, Q1 minus Q2 by Q1, that is 1 minus Q2 by Q1. This is the ratio, this is the equation to find efficiency. Okay, in a heat engine. Let's see what is a Carnot engine. Carnot engine. Carnot engine means it is a reversible engine. It is a reversible engine operating between two temperature. Okay. It is a theoretical engine. Carnot engine is a theoretical engine. Carnot engine is a theoretical engine. Theoretical. It is a theoretical engine. Theoretical engine. Okay. The four thermodynamic process involved in Carnot engine. I want everyone to know what is the thermodynamic process that is involved in Carnot engine. Okay. First one is isothermal expansion. Next is adiabatic expansion. It can be asked as a question. Next is isothermal compression. Next is adiabatic compression. Since Carnot engine is a reversible engine, it is an ideal engine. It is an ideal engine. In Carnot engine, we can write Q1 by Q2 is equal to T1 by T2. Fine. So we can write here eta is equal to 1 minus T2 divided by T1. Okay. Let's see refrigerator now. Let's see what is refrigerator. Refrigerator means it is a cold reservoir, and we are transferring, okay, Q1 heat. Okay, this is at temperature T2, whatever. Okay, and these are working substance. And this is the reservoir, hot reservoir, in which we are giving W work. Okay, so work, using that work, the working substance is working. Okay, and it is transferring Q1 heat from cold reservoir and giving a Q2, giving, so we can write Q2 here, sorry, Q2 here, sorry, Q2 here. Okay, it is transferring Q2 heat from cold reservoir and giving a Q1 heat to the hot reservoir. So using the external work that we are giving, the working substance is working and transferring a heat of Q2 from cold reservoir to, and transferring a net heat of Q1 to the hot reservoir. Okay, fine. So instead we can write Q1 is equal to W plus Q2. Fine. And W is equal to Q1 minus Q2 also. instead of efficiency that we have seen in Carnot engine or heat engine, here we have a term called beta, which is called coefficient of performance, which is equal to same output by input. What is output? Output is Q2. Q2 is output. Q2 is the output. And what is the input? We are given W. And Q2 divided by Q1 minus Q2. Or T2 divided by T1 minus T2. This is the equation of finding coefficient of performance beta. Okay, T2 divided by T1 minus T2. T2 divided by T1 minus T2. T2 divided by T1 minus T2. Like sometimes it can be asked, a refrigerator is this, it's having coefficient of performance. What will be the efficiency if it is converted into a heat engine, something like that. So you want to know the relation between beta and eta. Beta is the coefficient of performance and eta is the efficiency. And beta is equal to 1 minus eta divided by eta. So fine. So far so good. Okay. Now let's see some questions and we can solve the equation. Okay. See. 1 mole of an ideal gas expands at a constant temperature of 300 Kelvin from an initial volume of 10 liters to final volume of 20 liters. The work done in expanding the gas. So it is an isothermal work. We want to find isothermal work. Isothermal work, we know what is the equation. 2.303 work isothermal is equal to 2.303 nRT log V final minus V initial. V final minus initial. What is the V final? 20. What is the V initial? 10. So 8.31, that is R. What is the N? 1. 2.303 into 1 into 8.31, which is the R, which is given. Temperature 300 Kelvin into log V2 by V1. Log V2 by V1. What is log V2 by V1? Log 20 by 10. Log 2. Log 2 is equal to 0.3. So net we'll get 1728 joule. Easy. See, what is the isothermal work done? What is the isothermal work done? Work isothermal is equal to 2.303 nRT log V final minus V initial. We use this equation to solve this question. Fine. The amount of work done in an adiabatic expansion from T to T1. What is the adiabatic work? Work adiabatic is equal to NR T initial minus T final divided by gamma minus 1. What is the N is not given, so we can write N is equal to 1. So answer is R divided by gamma minus 1. What is T initial by T final? T initial. What is the T initial? T divided by T final T1. So answer is option B. Okay, fine. Option B. A gas for which gamma is equal to 1.5 suddenly compressed to 1/4 of the initial volume, then the ratio of final to initial pressure. I already told you, instead of saying adiabatic process, they will say sudden bursting, sudden expansion, sudden compression, etc. Okay. When you see sudden compression, sudden expansion, sudden bursting in the question, we should understand it is a adiabatic process. And we know what is the equation of adiabatic process. PV is a constant. PV is a constant. PV is a constant. So we can write P1 by P2. Ratio final to the initial. So P2 by P1. P2 by P1 is equal to V1 divided by V2 raised to gamma. What is V1? V1 suddenly comes to 1/4. So V1 by V2 is equal to 4 by 1 raised to 1.5, 3 by 2. So it is 8 by 1, 8 is to 1, option D. So an ideal refrigerator has okay, how many questions remaining? 4 more questions, okay, fine. An ideal refrigerator has a freezer at a temperature minus 13 degrees Celsius. The coefficient of performance is 5. The temperature of air to which heat is rejected will be. Beta is given 5 and at a temperature of minus 13 degrees Celsius freezer. So T2 is given. What is the equation of beta? What is the equation to find beta? Beta is T2 divided by T1 minus T2. T2 divided by T1 minus T2. What is T2 now? What is T2? 273 minus 13, 260 divided by, we don't know, T1 we don't know, T2 we know. Okay. So 260 is equal to 5T1 minus 1000 5 into 200,000, 60 into 5, 1300. So 1560 is equal to 5T1. T1 is equal to 56 divided by 5, which is 3112 Kelvin, which is equal to 39 degrees Celsius. Yes, we have the option. Fine. Efficiency of a Carnot engine. Efficiency of a Carnot engine is 50%. When temperature of outlet is 500 Kelvin, in order to increase efficiency up to 60%, keeping the temperature intake same, what is the temperature of the outlet? So see the question now. It have like see. Like it has been mentioned that efficiency of Carnot engine is 50%. Efficiency of Carnot engine is 50%. Okay. When temperature of outlet is 500 Kelvin. What is outlet and inlet? Outlet. Okay, 500 Kelvin. In order to increase efficiency up to 60%, keeping the temperature of intake same, what is the temperature of outlet? Temperature of outlet. What is the equation to find eta? Eta is we know 1 minus T2 divided by T1. So what is eta? Eta is 50%. That is 1 by 2. 1 by 2 is equal to 1 minus T2. T2 is 500 by T1 we don't know. So T1 is 1 minus 1 by 2. T1 is 1000. Okay. Now, in order to increase efficiency to 60%, 60% means 6 by 2 is equal to 1 minus. Now we want to find the new temperature of outlet, that is T2. T1 we know 1000. 4 by 10 is equal to T2 divided by 1000 and T2 is equal to 400 Kelvin. The efficiency of Carnot engine operating between reservoirs maintaining at a temperature 27 degrees Celsius and 123 degrees Celsius, minus 123 degrees Celsius. Simple. Eta is equal to 1 minus T2 divided by T1. 1 minus 27 degrees Celsius. 27 degrees Celsius. 273 plus 27. Always temperature always should be in Kelvin. So 300, sorry, T2. 273 minus 123, 150. Divided by 273 plus 27, 300. 1 minus 1 by 2. 1 by 2. 50%. A given system undergoes a change in which the work done by system equals the decrease in its internal energy. The system must have undergone an. The question is given that the change in which the internal energy change is equal to work done. So system must have undergone what type of change, what type of process, which means delta U is equal to W. Maybe it's W. We know delta is equal to W. It can be minus W. Okay. So it is seen in delta Q is equal to 0. So it is an adiabatic process. Adiabatic. Adiabatic process. It is given that delta U is equal to W, and we know in adiabatic process. See, in adiabatic process I already mentioned delta U is equal to minus W, and Q is equal to 0. Q is equal to 0. So delta U is equal to W in adiabatic process. Okay, fine. So we have almost completed the thermodynamics part 2. Okay. So I hope I almost discussed the important topics, not the every topics, important topics. Majority of the questions will come from this area. Okay. Zeroth law, heat, work, internal energy, first law of thermodynamics, second law of thermodynamics, that is Clausius statement, Kelvin Planck statement, heat engine, refrigerator, reversible process, irreversible process, Carnot engine. The 4 types of process are in Carnot engine is isothermal compression, adiabatic compression, isothermal expansion, adiabatic expansion. We should know all those things. Zero of thermodynamics, heat, work, internal energy, reversible process, heat engine. And we have seen some questions, work isothermal, work adiabatic, and the relation of adiabatic, that is P V raised to gamma is a constant, and heat engine, refrigerator, the relation between beta, eta. Okay, so we have almost finished everything. So if there is any doubt, you can put in the comment section. So I'm wind upping today's session. So we can see with the next session. Okay, thank you.